All right, this video is to review key parts from acid-base stuff you may or may not remember. So before you take the Kung Fu quiz, what you want to do is make sure you review this or watch this, what you're kind of doing now, to kind of hit on our highlights and things you may have forgotten. First of all, we know what a weak acid is. It barely breaks apart, okay? So that means they have Ka values because strong acids don't have Ka values. One thing they ask you to do is figure out which one is going to be stronger than the other. The way that works is you compare Ka values. So if you compare Ka values for acids, the larger the Ka, the stronger the acid. So you see how this is to the -4th and that's to the -4th. 6.8 is larger than 4.5. That would make hydrofluoric acid or weak acids the strongest. So when you go to compare weak acids, the larger the Ka value, the more product favored it is, means the stronger the acid because it ionizes more. Amphoteric comes up. If you remember during chapter 15, amphoteric means that it can either gain an H according to Bronsted-Lowry or lose an H. Remember, Bronsted-Lowry acid or base gains or loses an H. So like if you look right here, you have HNO3 and water. HNO3 is going to transfer an H over here. So that makes this a Bronsted-Lowry acid. This is a base, and you get HCl plus there. In this one, NH3 has 3 H's. Water has 2. Water transfers an H to NH3, making NH4 and creating OH minus. In this case, this is the acid, and this is the base. So if you notice, this reaction water is a base. This reaction water is an acid. So when you say something's amphoteric, it means you can either take an H or give an H. Now, first and foremost, it has to have a hydrogen. If it doesn't have any hydrogen in it, that means it obviously can't be amphoteric because it can't give an H. The other thing is, besides water, everything else is negatively charged. So if you're looking for something that's amphoteric, it has to have an H. If not, scratch it out. And it has to have a negative charge so you can tack an H on there, with the exception of water, because we know water, based on the reaction right here, can either take an H or give an H. All right. pH. Got to be able to find pH on the free response. Also multiple choice. There's an easy, quick way to do it. All you have to do to find pH for a strong acid or a strong base is count decimal places. For example, if I look right here, this tells me the molarity is 0.1 molarity HNO3. So when I get to the first digit that's not 0, I'm counting the number of decimal places. The decimals here, I go over 1. It has technically 1 decimal place before I hit a digit besides 0. That means if I take the negative log of this, since it's 0.01, the pH is actually going to be 1. If I had 0.001 HCl, 1, 2, 3 decimal places. If you take the negative log of that on your calculator, you wouldn't have a calculator on the multiple choice, but if you take the negative log of that, you would get a pH of 3 when you take the negative log. So if it's a strong acid or a strong base, if it's a strong base, obviously you can count the decimal places and find pOH. You would still subtract it from 14, but it's a quick, easy way to find pH because that's the way they give it to you on the exam. They'll give you 0.01, or they could give us 0.01 right there. 1, 2 decimal places, that's going to have if it's an acid, it's going to have a pH of 2. If it was a base, it would have a pOH of 2, and you could subtract it. So that's a quick way to do strong acids and strong bases, is we just count the decimal places till we hit a digit. Now, weak acids and bases use the shortcut, I didn't write it there, shortcut, and put the numbers in scientific notation to solve. Remember, a weak acid is x squared over molarity is equal to Ka. Without an ice table, a weak base is x squared over molarity is equal to Kb. They will have you solve some of these on the exam. The trick is, if they give you the value for x and they give you the value for m or Ka, make sure all the numbers are in scientific notation. Make sure put all the numbers in scientific notation, and then the math, you can simplify them based on the math. But you have to be able to solve, even if the numbers are in scientific notation, it's pretty easy. Like if you divide the two front numbers, the mantissa, and then you subtract the exponents. That's how you do it when you divide in scientific notation. I'll go over that in class a little bit to kind of help you out over some of the problems. But as you're doing some of the weak acid, weak base problems tonight on the Kung Fu quiz, set it up. X squared over molarity is equal to K. X squared over molarity is equal to Kb. Put the numbers in scientific notation. See if you can solve it again without a calculator. Buffers. They do mention buffers a lot. You need to know the definition. A buffer is a solution that resists changes in pH, either up or down. So you can add H plus to it, OH minus, it resists changes in pH. Buffers consist of typically two things, a weak acid and its salt, or a weak base and its salt. That's what you're looking for. They commonly have you identify buffer solutions on the exam. If you look, first thing you do is cancel the heartbreakers. If I look right here, K is a heartbreaker. I'm good. I have a weak acid as HF, and F minus is its salt. So this would count as a buffer system. So that would be a buffer system. If I look here, K is a heartbreaker, B is a heartbreaker, BR. The only thing I'm left with is H plus. So all that is an acidic solution. There's nothing to take care of. Remember, a buffer has to have a component that takes care of the acid and the base. So you have to apply this several times. The only other condition where you would get that, like if we look right here, which of the following of these are buffer solutions? Well, heartbreakers. Gone, gone, gone. The only thing I have is a solution with H, so that's a very acidic solution because it's a strong acid. If I look here, heartbreaker, 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 so that basically is going to be salt water, pH of 7. Here, heartbreaker, I have CN minus, HCN is a weak acid, so I have a weak acid and it's salt or conjugate. So the pH of any weak acid solution is going to be around probably 3 to 6, generally, unless it has a high molarity. So you want to remember that. pH of a weak acid is going to be about between 3 and 6. Look at D. So that's one that technically counts as a buffer solution. These do not. If you look at D, what do you notice? I have a weak acid and a strong base. I cancel the heartbreaker, so I have OH and HF. The key is sometimes you can take a weak acid or a weak base and you take a strong, in this case OH. If you have half the molarity, it means you're halfway to equivalence. Remember, when you're halfway to equivalence, you have the exact same amount of salt as the acid or the base. So technically, this makes a buffer solution. So this makes a buffer solution. You have to be aware of it because it does come up. So if you do see a weak acid and you see the molarities are exactly 1/2 of each other of the weak, then you could make a buffer solution by that. So that is something you have to be aware of. Which two parachemicals will produce a buffer solution right here? If we look, heartbreaker, HF, F, boom. This is going to be a strong acid and a weak base. That is not a buffer solution. HF and HC3O2, those are two weak acid solutions, so the pH is probably going to be like between 3 and 6. This is another weak acid and a weak base. Oh no, I'm sorry, strong base. And that could possibly make a buffer solution if the molarities were half, but they don't give you molarities. That's why A is the correct answer. So A automatically, I have a weak acid and a salt or an ion, and a weak base and a weak base and a salt, which isn't up here, but you get the idea. Next thing that comes up, buffers. How we pick buffers? Well, the effective buffer range is always plus or minus 1, right? We use pKa. This is why we use pKa. We choose a weak acid or a weak acid with a pKa closest to the desired pH of the buffer. That's how we pick buffer solutions. So you need to be able to do pKa. Problem is, if it's on the multiple choice section, you don't have a calculator. So what do you do to get pKa? Well, here's what you do. You can assume or ballpark based on the exponent. I just take the exponent and turn it over into pKa. -5, that means I'm going to have a pKa of about 5. -4, I'm going to have a pKa of 4, we'll say, roughly. Rough estimate. This is 2. My pKa is going to be 2, and my pKa is going to be 6. And on the AP exam, they'll even give you a little bit more disparity between the numbers. I'm looking for a buffer that works with a pH of 3.2. What's the closest number? The closest number that is going to be C. So the best acid, whatever acid would be listed, whatever that would be, that has a Ka of 6.0 times 10 to the -4th, would have the pKa closest to the 3.2. So I would select that as my buffer system. That's what I would use to prepare my buffer. Equal amounts of each, equal moles of the acid, and its salt would produce an excellent buffer system. Acid-base neutralization. Whenever they mention the word neutralization, they're talking about an acid and a base canceling each other out. What you have to watch for on the AP exam is this. You got to remember to pay attention to the number of H's and the number of OH's. You have to account for them. So if they give you something like Ca parentheses OH parentheses 2, you got to pop that number in there because the molarity is actually going to be double what you think it is. If they give you something like H2SO3 with the two H's there, you have to account for it there. If they're both 1-to-1 with regard to H and OH, then you just plug in and you solve for the missing value. Yes, you would be expected to do it without the calculator, but the biggest thing you have to pay attention to is typically on a neutralization problem, if it's not in the free response, they'll give you something with double OH's or extra H's, either one. So pay attention to that. Last thing is, how do we pick an indicator? When you pick indicators for titrations, like we did when we did our titration curve, you pick the indicator so it changes color after equivalence. At equivalence or after, right around that range. So at equivalence or just right after, that's the idea. So if you notice, you're titrating a weak base in this problem with a strong acid. We know that the only titration that has a pH of 7 at equivalence is a strong acid, strong base. Whenever you have a strong base, weak acid, a strong acid titrating a weak base, what's going to happen is it would look like this. The curve would look like this, go down like this. Here is, that would be the actual equivalence point is going to be somewhere around here. It's going to go down more like this. This is going to be 7 right here. It's the equivalence point is going to be below 7. Why? Because if you titrate NH3 at the end, when you completely cancel it out, you leave NH4 plus in solution. Because when you cancel it with the H and H plus, the reaction is going to be a strong acid reacting with NH3. I'm going to get NH4 plus, the salt of a base. A positive ion acts as an acid. So at equivalence, it's going to be below 7. A little bit below 7. That's why my correct indicator solution for my titration would be methyl red, because of a pH of about 4 to 6. That's when you get your color change. All right, that's it for tonight. Go ahead, take the Kung Fu quiz. Remember, you only have 2 more after this. Have a good evening. Stay out of trouble.